Hello there, Mr. Sutton here, bringing you the BC Calculus 710 Extra Practice number 3 solutions on alternating series test. For this problem, we want to know if this series converges absolutely, conditionally, or diverges. So we first consider the absolute case, just basically all this stuff without this -1 to the n plus 1 stuff. So to figure out convergence for this series, this is a tricky one. If you use the nth term test, you'll see that the limit goes to 0 as n goes to infinity. It's not a p-series. We can't use alternating series test yet, maybe down the road if all else fails. So this is one that you really have to use the integral test on at this point. There isn't anything else unless you have a comparison test handy. So first let's verify we can use the integral test. 1 over n ln of n. This is a continuous function. It's positive and it's decreasing for n values that are greater than or equal to 2. And so, the only issues you'd have here is if you had 0 for n, or if you plug in 1 for n, ln of 1 would be 0, and that would be an issue. But for 2 or greater, we're good. And again, since the limit as n approaches infinity is 0, this thing is decreasing. So we are allowed to use the integral test on this. So we're going to take the integral from basically 2 to infinity of this thing. But since that's an improper integral, I'm just going to skip straight to the limit version of that. So limit as b approaches infinity of the integral of 2 to b of 1 over ln of n, n ln of n, dn. Too many n's in there. So for this is one if you've done this in the past, you remember that you had to use substitution. Basic idea is we have a function and its derivative in the same problem. The derivative of ln of n is 1 over n, which we can use against this n down here. So that's the direction we have to go when we integrate this. So I'm going to let u equal ln of n. So then du is going to be 1 over n dn. And then isolating dn, we have n du is equivalent to that. We also have to turn these limits of integration, which are currently n values, into u values. So if n is 2, then u is ln of 2. And if n is b, then u is ln of b. Converting all of this over now, we have the limit as b approaches infinity of the integral from ln of 2 to ln of b. And we're going to have a few other changes here. This ln of n is going to be a u, and instead of dn, we're going to write, let's see here, n du. So all those changes. Limits of integration got changed. ln of n is now u, and again, we have n du instead of dn. So these n's here are going to cancel. We end up with 1 over u du, which we can now take the antiderivative of with respect to u. That's going to be ln of absolute value of u. And we still have limit as b approaches infinity, and we're still evaluating from ln of 2 to ln of b. So this is going to be ln of b minus ln of 2. And I no longer need the absolute value here. For b values, we're going to infinity here, so we're not worried about plugging in negatives there anyway. So as b approaches infinity now, what's happening? Well, ln of b is a very slowly growing function. Ln of that is even more slowly growing. But as we go to infinity, this first term goes to infinity, so that infinity's out everything here. So because our integral does not have a limit, it diverges. That means the series diverges, at least the absolute value version of the series diverges by the integral test. So we go back to considering the alternating version of the series. And when we do that, we see that first off, it is alternating. And also, the terms are decreasing, in absolute value at least, all the way to 0, because the limit as you approach infinity of 1 over n ln of n is 0. So because our terms are alternating, decrease in abs value to 0, that means that the original, at least, is going to converge conditionally by the alternating series test. On this problem, trying to find the interval of convergence for this series, because this is not a geometric series, I'm going to have to use the ratio test for that. So I'm going to take the limit as n approaches infinity of the absolute value of, and I need the n plus 1th term over the nth term for this expression here. The only good news here is that I don't have to keep this -1 hanging around right now because I'm putting everything inside absolute value. So n plus 1th term, we've got x minus 1 to the let's see here. This is going to be 2 parentheses n plus 1 plus 1. So that would be 2n plus 2 plus 1, or 2n plus 3 if you simplify. Down here you also end up with 2n plus 3. So we have, and I guess I'll simplify that a little bit later, but that's where we're going with all that. So now we also have the nth term down here. That's basically this whole summand without the negative 1 to the n. So now same change flip. We've got x minus 1, and now I'll simplify this to 2n plus 3. We also have this 2n plus 1 from down here. And we also have a 2n plus 3 from right here times x minus 1 to the 2n plus 1. So these x minus 1s are going to reduce. Subtracting the exponents, we end up with just x minus 1 squared in the numerator. And we still have a 2n plus 1, and downstairs we also have that 2n plus 3. So as n approaches infinity, this plus 1 can be ignored. So can this plus 3 down here. So we have 2n over 2n, and the only difference is that we still have an x minus 1 squared up here, which this whole squared parentheses is treated as a constant at this point. So as n approaches infinity, we can actually just cancel out those 2n's, so we just end up with x minus 1 squared inside the absolute value. So the series will converge if this nth ratio is less than 1. And let's go ahead and solve for x now. So I can square root both sides. So x minus 1 is absolute value is less than 1. And then rewriting this without the absolute value, I have negative 1 less than x minus 1 less than 1. And then finally adding 1 everywhere, we have, let's see, this will be 0 less than x less than 2. So this is kind of our first draft, our rough draft of the interval of convergence. Since we got this, though, using the ratio test, we don't know about the endpoints yet. We're going to have to test out 0 and 2 in the series and see if the series will converge at those x values. So let's test 0 first. If I plug 0 in here, this is going to be a negative 1 to the 2n plus 1. And times this negative 1 to the n, that ends up being a negative 1 to the 3n plus 1, which is kind of weird. Still over 2n plus 1. So the first thing I notice about this series is that this is alternating, and also if you take the limit as n approaches infinity, you'll see that this thing is decreasing to 0 because it's bottom heavy. Only the bottom is really growing here. But before I go ahead and write out my justification, let me take a look at the other endpoint just to see if we have another alternating one. So at x equals 2, this expression is going to be, let's see here, this is going to be 2 minus 1, which is just 1 to the 2n plus 1. We can just ignore all that. We still have this negative 1 to the n, though. So we have negative 1 to the n over 2n plus 1. So we see here that actually both of these series are alternating and decreasing in absolute value to 0. They're alternating and getting closer and closer to 0 as n increases. So therefore, both of these are going to converge by the alternating series test, which means since both of our endpoints actually converge, we have to rewrite our interval of convergence as 0 less than or equal to x less than or equal to 2. For this free response problem, we're given two functions. F is defined by this power series up here, and we also have a g function defined by g of x right here. First task is to find the interval of convergence for f and justify the answer. So taking a look at f, looking at the general term here, I notice that this is not a geometric series. We don't have exponential terms everywhere here. So I'm going to have to use the ratio test to get the interval of convergence. So that's going to be the limit as n approaches infinity of the absolute value of, and now we have a huge fraction. Up top we have the n plus 1th version of this. Down below we have the nth version of this. So up top, n plus 1 version, and by the way, we're going to leave out the negative 1 because we're dealing with absolute value here. So we're going to have n plus 1 times x to the n plus 1 all over n plus 2. So that's the n plus 1th version of our term here. And down below we just have the nth version, which is just going to be all of this stuff in the general term without the negative 1 to the n. Because again, we're putting this inside an absolute value, so that's going to go away anyway on its own. All right, same change flip to reduce this. we've got n plus 1 times x to the n plus 1 times another n plus 1 down here. So n plus 1 squared, if I want to write that a little more succinctly. And down below, we've got n plus 2 times n times x to the n. So it looks here like these x's can cancel, or at least reduce. So we just have a single x in the numerator, along with that n plus 1 squared. And in the denominator, we just have an n plus 2 and an n. So as n approaches infinity, I can forget about this positive 1 here, and also this plus 2. So I really just have n squared x over n squared. N squareds are going to cancel, just leaving me with absolute value of x. For the series to converge, this nth ratio that I just found by taking the limit, this has to be less than 1. And I can rewrite this to get an interval of convergence without the absolute value as -1 less than x less than 1. But of course, that's not the end of the story. Because we got this using the ratio test, we don't really know whether or not we converge at these endpoints. So we have to test -1 and 1 out into the function to see if we converge there. So plugging each of these individually into this general term, if x equals -1, f of -1, we can write this as, well, let's see here. This would be a -1 to the n times another -1 to the n. That would be a positive 1 to the n, which would essentially just go away, leaving us with n over n plus 1. Well, if our series is n over n plus 1, let's just go ahead and use the nth term test on this to see what happens. The limit of this thing as n approaches infinity is just going to be, well, we can forget about this 1, so n over n equals 1, and that's not 0. So this actually diverges by the nth term test. Now let's test out the case where x equals 1, the other endpoint. F of 1, going back up here, we're going to have 1 to the n, which is just 1, so we can forget about it. We still have a -1 to the n times an n over n plus 1. And on this one, it is alternating, but you got to be careful here. My knee-jerk reaction is to use alternating series test on this, but we also have to be decreasing an absolute value to 0. What happens if we take the limit of this thing? The limit of this, as n approaches infinity, is actually going to be plus or minus 1, because you still have, when you get rid of this 1 down here, you still have n over n. So because we have plus or minus 1, really because we don't have 0 for that nth term, this is also going to diverge by the nth term test, so that we don't converge at either of the endpoints. Our final interval of convergence then is going to be -1 less than x less than positive 1. For this part of the problem, they tell us that the graph of y equals f of x minus g of x passes through the point 0, -1, and they want us to find y prime of 0 and y double prime of 0, and then determine whether we have a relative min, max, or neither at x equals 0. Okay, so let's start by writing out a function for y, basically, using f of x minus g of x. Now, in order to find y prime and y double prime, eventually I'm going to need to know the linear and quadratic terms of these two series that I'm constructing this out of. So I'm only going to construct this far enough to get to the quadratic term. After that, I don't really care. So y equals, then, we can write f of x, so -x over 2 plus 2x squared over 3, because, again, I don't really care about anything after the quadratic term. And then we're going to be subtracting all this stuff from g of x, so -1 plus x over 2 factorial minus x squared over 4 factorial, and a whole bunch of stuff I don't care about. And I'm going to think of 4 factorial as 24 there, 4 times 3 times 2. That'll help me on my next step. For my next step, to figure out the true coefficients of the linear and quadratic terms, which again I need to figure out y prime and y double prime, I'm going to combine like terms. So I've got a -1 that's kind of on its own. I have a negative x over 2 and a positive x over 2. Those are going to cancel out, but I am going to write 0x here. I don't have to, but this just really reminds me that I have a coefficient of 0 for my linear term. And then we have a 2/3 x squared minus 1/24 x squared. Well, this is really like 16/24 minus 1/24, which is going to be 15/24, or 5 over 8 if we reduce that fraction. So we have positive 5/8 x squared. and again, a whole bunch of other terms we don't care about. So now the x coefficient, which is going to be equivalent to y prime of 0 in this case, is 0. So that answers the question of what y prime of 0 is. For y double prime of 0, we know that the way that Maclaurin series are constructed, y double prime over 2 factorial equals the coefficient of x squared. Well, the coefficient of x squared here is 5/8. So this stuff here, y double prime of 0 over 2 factorial, since it's equivalent to the 5/8 that we see in the actual series, we can just move things around a little bit to solve for y double prime of 0. So just multiplying both sides by 2 factorial, that just gives us 10 over 8, which we can reduce to 5 over 4. So that answers the question of y double prime of 0. Now they wanted to know if we had a min-max or neither. Since we only have information about this function at x equals 0, we are going to have to use the second derivative test to get to the bottom of this. So the first derivative is 0. That being the case, because the second derivative is positive, because in other words, we have a concave up function, that means since we have a critical value there, we're at the bottom of the cup. So that means we have a relative min at x equals 0 for this function. For this function, we have a function f with a Taylor series that converges to f of x for all x in the interval of convergence. We know that f of 1 is 1, f prime of 1 is negative 1/2, and then the nth derivative at x equals 1 is this crazy expression for all values of 2 or greater. So they gave us kind of the first two crucial values for f for free, and we're going to have to earn the rest of them. So based off of all this, our first task is to write the first 4 non-zero terms and general term of our Taylor series about x equals 1. So our first term is just going to be f of 1, which in this case is just 1. Next term is going to be f prime of 1 times x minus 1. So that's negative 1/2 times x minus 1. And all of these are going to have an x minus 1 in them now. The exponent on the x minus 1 is just going to keep going up. So for the next term, we're going to have f double prime of 1 times x minus 1 squared over 2 factorial. So what's f double prime of 1? To figure that out, we have to go to this f formula over here, derivative formula, and plug 2 in for n. So if we do that, this negative 1 is going to become a positive. We're going to have 2 minus 1 factorial, which is just 1. And we're going to have 2 to the 2, which is 4. So when the dust settles, this is just positive 1/4 times x minus 1 squared. And we still have a 2 factorial down there hanging out with the 4. Because this 2 factorial always comes with the quadratic term of a Taylor series. All right, and we only have one more to go for the first 4 non-zero terms. So for n equals 3 now, we're going to have, let's see, negative 1 to the third is a negative, and this is going to be 3 minus 1 factorial, so 2 factorial, so basically 2. We have a 2 to the third down here, which is 8. So 2 over 8 reduces to 1/4. So we have minus 1/4. And then we still have a 3 factorial down there and an x minus 1 cubed. All right. So, and then we have the general term. And I guess I didn't reduce this here, but you didn't really need to at this point. I'll do that in just a moment. So our general term for this one, usually the general term is kind of a pain, but here it's actually sort of easy. So we know we're going to have an x minus 1 to the n. We know we have to divide by an n factorial. And for the nth derivative, we can actually just kind of cut and paste this formula right here. So we have negative 1 to the n minus 1 factorial. We have the x minus 1 to the n that should have been there anyway. We have this 2 to the n that was down there from the derivative, and the n factorial that's always in the general term of a Taylor. And if we really wanted to, we could maybe clean this up a little bit. So if I wanted to, for example, I could write this 4 times 2 is an 8, and this is really, let's see, 1 over 8 times, no, 1 over 4 times 6, so that's 1/24 for that term. But it's up to you whether you simplify the coefficients. For this part of the problem, we're told our Taylor series has a radius of convergence of 2, and they want the interval of convergence. Well, if I'm going down this whole interval of convergence road, I want to write this in sigma form, just so it's a little bit easier and more compact to look at. So for that, I'm going to need the general term of a Taylor series with this derivative thrown in. So I'm going to have the nth derivative times x minus 1 to the nth over n factorial. So basically, summation from 0 to infinity of all of this stuff, my nth derivative, times, and again, we're going to have n minus, or x minus 1 to the n over n factorial. Now, I can clean this up just a little bit here. The n minus 1 factorial and the n factorial can reduce a little bit. N factorial is really just n times n minus 1 factorial. So if I reduce those, I'm really just left with an n down here. So when the dust settles, then I have a negative 1 to the n, I have an x minus 1 to the n, and I have a 2 to the n times n. All right, so this is what I'm dealing with. Now, before you go all ratio test on this thing, hold up. They already gave you the radius of convergence, which is really what you're using the ratio test to find. Since you have a center of 1 and a radius of convergence of 2, you actually have everything you need to at least find the interval of absolute convergence. So we know that when we're writing our kind of our rough draft of the interval of convergence, it's going to be 1 minus 2 for the left endpoint, so negative 1. So that's going to be less than x is less than, and now 1 plus 2 gives us the other endpoint of 3. So this is not the final interval of convergence necessarily, but it's the starting point. Now, because we would have had to use the ratio test to get this if we did it the long way, we have some ambiguity at those endpoints, and we have to test them to see whether we converge at negative 1 and 3 or not. So if we test out x equals negative 1, and I'm going to test it in this version of the summation here, that's going to give me, let's see here, we're going to have a negative 1 minus 1, that's negative 2 to the n. I can combine that with this negative 1 to the n to get basically a positive 2 to the n upstairs. But hold on a sec. We have a positive 2 to the n downstairs too. So those are going to cancel. And all I'm left with when I simplify is just 1 over n. Well, we know what this series is. This is the harmonic series, which is known to diverge. So not a whole lot of proof needed on that one. So we know that we are not including the endpoint of negative 1. Well, how about the endpoint of 3? What's f of 3 going to come out to? So that's going to be 3 minus 1, which is, we have a 2 to the n. That's going to cancel out with this 2 to the n down here. So we just have a negative 1 to the n over n. Now this one we also recognize. This is the alternating harmonic. Or you could use the alternating series test on this. Terms alternate, decrease in absolute value to 0. Therefore, this converges by the alternating series test, but you could have said this was the alternating harmonic and automatically converges. Either would have been acceptable here. Either way you slice it, we know that we have to include our endpoint of 3, so we're going to write this as negative 1 less than x less than or equal to 3. For this part, they said that the Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Okay, if they say so. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So just to recap from part A, where we actually wrote out some of the terms, here's what we had from part A. We had f of x equals 1 minus 1 half x minus 1 plus 1/8 x minus 1 squared, yada yada. We've got some more stuff there. But they just said use the first 3 non-zero terms to approximate f of 1.2. So this is where you got to be super careful. We're going to write f of 1.2 is approximately equal to the following. We have 1 minus 1 half times 1.2 minus 1 plus 1/8 times 1.2 minus 1 squared. Basically, all this stuff with 1.2 replacing x. And we're only doing that for the first 3 terms. And again, writing approximately equals. If you don't write this approximately equals, you do not get this point. So we're actually done. You don't have to go any further. You've got all constants here. But if you wanted to simplify this a little bit, this is going to be 1, and we're going to have minus, let's see, this is 0.2, half of 0.2, so we're subtracting 0.1. And over here, we have 0.2 squared, which is going to be 0.04. 0.04 times 1/8, what's that going to be? Well, that's like having, let's see here, 1/8 of, that would be 40 thousandths, so that's going to be 5 thousandths or 0.005. Again, you didn't need to simplify, but if we wanted to, we've got, let's see here, this is going to be 1 minus 0.1 is 0.9. Adding another 0.005, we've got 0.905. So that's the final simplified version of this. For the final boss battle of this free response, they want us to show that the approximation from part C is within 1,000th of the exact value of f of 1.2. So to help us with this, let me write out a little bit more of my function from part A. So we're really getting a lot of use out of that function we wrote in part A. Hope we actually got that correct, right? We're told in part C that if I plug in 1.2 to the first three terms of this, I get an alternating series. And if we notice, beyond alternating, these terms, if you plug in 1.2, these terms are actually decreasing as you go, and they're decreasing in value to 0 if you were to actually take the limit as n approaches infinity of all this. You're just going to have smaller and smaller things because your exponent is going up, and you're just doing 0.2, a number less than 1 each time around. And also these denominators are growing. So in general, we can say that our terms alternate and decrease in absolute value to 0. Now the reason I threw in this extra term from part A that I didn't bother using in part C was because when you have an alternating series like this, the error is bounded by the absolute value of the next term. This is the alternating series error bound we're using here. So to see what my error is, my error is going to be less than the absolute value of 1.2 plugged into this very next term right here. So I'm just going to write error is less than absolute value of, and I can ditch the negative now because I have absolute value. So I can just write 1 over 24, and in here I'll have 1.2 minus 1 to the third. Well, to show that this is less than 1,000th, or is no more than 1,000th, I actually have to evaluate this a little bit until a reasonable person can see that how this relates to 0.001. So one thing I'll do here, let me first do 1.2 minus 1. That's going to be 0.2. And if I raise that to the third power, well, let's see, 0.2 times itself would be 0.04, times another 0.2 is 0.008. Now, to make my life easier, and this will actually make things easier, I'm actually going to turn that into a fraction. I'm going to call that 8 over 1,000, because that's really what it is. 0.008 is really just 8 thousandths. And the reason this makes my life easier is because now I can do something with this and the 1 over 24 to come up with a single number. So the 8 and the 24, those can cross-cancel here, because we have multiplication going on. So I can rewrite this as really just 1 over 3 times 1 over 1,000. So that's 1 over 3,000. Now, 1 over 3,000 has a larger denominator than 1 over 1,000. So therefore, it is a smaller fraction than 1 over 1,000. So therefore, this is smaller than that error bound they wanted of 0.001, which is just another way of saying 1 over 1,000. So here we've proven what we set out to prove. We've got our approximation within 0.001 of the exact value, so we are done.